Imagine you have this unit square and they ask you to put 25 square tiles inside this square. What is the biggest size for a square tile? Of course, you do this and the size is going to be 0.2. You don't have any empty space, and that is going to be the largest possible size for the 25 tiles. But what if they ask you to do this for 5 tiles? In that case, you do this and the biggest size is going to be 1/3. You cannot use a larger tile for this arrangement. But what if I tell you you can do better than that? And no, I don't mean to use a hydraulic press to squeeze the tiles and empty some space. We are going to only use geometry. And that is how we do it. We have 5 tiles. Each one has a size larger than 1/3. And that is the problem of square packing. Let's see how it works. There are two ways to approach this problem. One way is to say you have a unit square and you are looking to find the biggest size for, let's say, 25 square tiles to pack inside that unit square. And your answer is 0.2 for the size of the tile. Another way to approach the problem is to say that you have a unit size tile and you want to find the smallest square to contain 25 of those tiles. Then you say the smallest size of the square should be 5. As you can see, these are equivalent and the ratio of the two sizes are the same, is 1:5, and it's just different approach for the same problem. The system on the left is what some websites like wolframalpha uses, and the system on the right is what you see in some articles like the one in Wikipedia. Here we are going to use the system on the left. If you need to get access to wolframalpha article about square packing, you just go to Google and search for wolframalpha. Then the first link that you see is the website. When you go there, you search for geometric packing. And that gives you all sorts of problems related to geometric packing. Go to the square packing, and then you have a template that you can use to find the best square packing for any number of tiles. It gives you the densest packing, the regular packing, the sizes of that, and you can change it to any other number, and it just shows you the result. But how do you solve this problem? The first way to do it is to use a diagonal strip of squares at a 45-degree angle. The first example is what you already saw, the case for 5 tiles, and as you can see, the one in the center is rotated. The other example is 10 tiles, as you can see, like this, or 27 tiles, 38 tiles. These are the best solutions we know so far. If you note the corner for the case of 10 tiles and 38 tiles, one of them has only one tile in the corner. The 38 tile case has 4 squares in the corner, but in fact you can use the same configuration also for the 10 tiles, as you can see here. And as you can see, they both look the same. Another variation for this type of solution is, for example, the case for 53 and 68 tiles, and the strip in the middle at the 45-degree angle has 2 rows of tiles. Another type of solution is to use a 45-degree angle block. Let's see how it works. A regular type of packing for 28 tiles may seem to you like this, which has the largest size of the tile equal to 1/6. But in fact, you can do like this, and then you can have a tile which is a bit larger than 1/6. The same for the case for 40 tiles. You can do better by doing a center block at 45-degree angle and reach a larger size for the tile. The 45-degree angle doesn't have to be exactly in the center. You can use an off-center block. For example, the case for 26, the best solution is like this, as far as we know. And the case for 85 tiles, the best solution so far is like this. As you can see, the 45-degree block is not exactly at the center and is a bit off-center. And the next type of solutions are irregular patterns, which are the most difficult to find. Let's see some examples. For 11 tiles, you can do this, and the largest size is going to be 0.25 or a quarter. But you can also do this, which gives you a larger size for the tile. Another example is the case for n equal to 17, which again gives you 0.2 if you do it like this. But if you do it like this, which is irregular, you get something larger than 0.2. Similar to that, the case for 29, and if you do it in an irregular pattern, is going to be like this. The case for 18 tiles is interesting because it has 4 different solutions, all of them the same answer for the biggest size of the tile. One of them is like this. Another way you can do the arrangement is like this. The third way is like this. And the fourth way you can do the tiles is like this. They look different, but they all give you the largest possible size of a little bit more than 0.2, which is an interesting case. You have 4 solutions with the same maximum size for the tile. For 19 tiles, you can do this and it gives you 0.2, or you can do this and it gives you a little bit larger size than 0.2. Now let's see a couple of special cases. This is the case for 87 tiles. You may say there is nothing special about it, but if you zoom here, actually there is some space between the tiles. They are not packed completely together. So this is in fact a special case, and you have some empty space between the tiles. But this is still the best known solution so far. And the last case we see together is related to a conjecture. They said, or at least they thought, when n is n squared minus n, or is in the form of n squared minus n, you cannot use a tile with size larger than 1 over n. But then Lars Kleemann found the smallest known counterexample for 272 tiles, which looks like this. In this case, your tile has a size a little bit larger than 1 over 17. And that's the smallest known counterexample for this conjecture. So the conjecture is not true. For more videos like this, visit the channel, and thanks for watching.